I'm grateful to the organizing committee to giving me the opportunity to speak here. Of course, I will not talk about everything about molecules in motion, but I will focus on the electrokinetic phenomena, which I find a fascinating application and fascinating case of molecular motion. I will start with a more general introduction because there are both equilibrium and non-equilibrium molecular dynamics approaches to see motion or in general any transport. So I will first introduce that, and then I will present our simulations of electroosmosis, which led to the simulation determination of zeta potential. I will explain why it's important, and I will end up with the current research, which also uses electrokinetic phenomena, and that's capacitive deionization in graphene nanopores. So I will start directly with giving you examples of the electrokinetic phenomena and their application. And one of the electrokinetic, it's a family of closely related phenomena. And let's start with electrophoresis. In electrophoresis, you have a charged ion, or rather charged colloidal particle, and it can be micrometer sized. And if you apply a DC voltage between two electrodes, the particle, of course, will start to move, and you can observe the speed. There will be constant speed proportional to the size of the electric field, and the ratio gives you the electrophoretic mobility. So in this case, it's electric field which is applied. It's the velocity which is observed, and this is true even for the electroosmosis. And in this case, it's the solid phase which is moving with respect to basically immobile surrounding liquid. And the last thing is reversed if we do electroosmosis. In this case, you have solid surface. It can be a cylindrical capillary. It can be some planar space sheet. And again, the surfaces will be charged, and then there will be some counter ions in the aqueous solution. And you apply electric field from left to right, like between the two ends of the capillary, and it will cause a motion of the liquid. So the whole liquid and the whole volume of the pore will move in the direction depending on the surface charge and the electric field. So in this case, the solid phase is immobile, and it's the liquid phase that's immobile, but still it's electric field induced, and you observe the velocity. And there is this bottom row, which again, it's still about relative motion of oppositely charged phases. If you have a colloidal solution, the particles can sediment just due to gravitation, and you have a charged colloidal particles which sediment. Some charge will be very closely moving with the particle, and some part of the charge will be a bit mobile, will be a bit lagged behind the motion of those particles. So if you just let it sediment, so the particles will move top to bottom in your vessel, it will generate a difference in electrostatic potential top to bottom, and you can measure either the sedimentation potential or current top to bottom. So in this case, no electricity applied, but rather it's generated, it's measured. So and finally, like the analog of electroosmosis, if you have again this charged capillary, and you just force the liquid to flow, some plug flow, pressure gradient, simply non-electrostatically forced motion, you will again strip part of the charge to move, and that will generate again a DC difference or electric current, like left to right along the capillary, and that again can be measured. So basically these are the four phenomena, but the theory is unified for all of these processes. And you can say, okay, so I was talking that we have a motion of charged particles, but in fact many molecules are neutral, many surfaces are uncharged. So is it really so common to have some charged particle moving in between surfaces or in electric field? And I would say that yes, many molecules are neutral in vacuum. But if you insert them to a solution, and if there is some charge transfer between the molecule and the solvent, typically there will be some exchange of charge, and the molecules will become charged just due to interaction with the solvent. And particularly in the case of water, which has pH and some concentration of hydronium and hydroxyl ions, it's very common that molecules, particularly organic molecules which have oxygen and hydrogen, will become charged. So let's say here we have a molecule at the point at the pH when it's really neutral. So here we have missing hydrogen from the carboxylic group, but here we have extra hydrogen on this amino group. And if then you lower the pH, so there will be a surplus of H plus ions in the solution. They will simply react with the molecule, and the molecule will become positively charged. And the opposite, of course, happens at the high pH when there is a surplus of OH minus groups, and you are losing one hydrogen. And depending, of course, on the pK, etc., simply you have negatively charged molecules. So basically, both molecules as well as surfaces easily become charged, and the pH value where the molecules or surfaces are neutral is not the pH 7, but it's a specific material or molecule-specific pH value, which is called the isoelectric point or point of zero charge. And it really can vary. For titanium, which I will simulate, it's like 5.4. For quartz, the pH when it's uncharged is about only 3. So it's really material specific. So this is just to stress, charged colloidal particles are in fact very common thing. And so if we talk about motion of ions, maybe one of the first application you might think of course, will be something related to batteries, energy storage. And in fact, this is really a very important application, particularly nowadays when we have batteries which include polymers, and really the motion of ions and complex ions in these complex electrodes is definitely not trivial to explore. So definitely that's a big application, and things are much more complex in these polymer based batteries than in the old school sulfur, lead sulfur batteries. The opposite process can be something like if you apply the electricity, you can do electrolysis, or you can use it to do electrophoretic deposition. So in this case, you carry the particles from one electrode to the other, and the material adsorbs on the electrode. So it can be really as simple as the old school electrolysis, but also you can use some ions as carriers, like for example these clay nanotubes. And for example, in this application, it's for titanium, basically implants. If you want to improve the healing of the implantation of the artificial joint, you can deposit in the titanium material also some basic antibiotics or some organic substance which prevents inflammation, etc. And as you already know, if you choose proper pH for this process, you will have even the biomolecule charged. It will somehow stick to this carrier, and you can electrodeposit even organic material to this titanium alloy. Big application of electrokinetic phenomena is electrophoresis. It's absolutely standard technique for the biologists who use it to determine the molecular weight of different substances. And it's particularly used for DNA because, as we have learned yesterday, DNA is charged due to the phosphate groups, so it's negatively charged. So of course, it will be very ready to be transformed through very narrow capillary between two electrodes. And particularly if you use some enzymatic chopper to split your DNA into chunks, you can even do full sequencing of the DNA and really see what's the series of your amino acids in the DNA. So really biologists use either this simplified electrophoresis where you just see the layers of substances with a different molecular weight, or the even modern sequences. That's really a very common application. Also, more and more, we want to have some quick analysis in medicine or biology, like, for example, to measure your glucose level, etc. And those devices can also profit from electrokinetics because it's a nice method how to separate something based on its charge, and the charge depends on the biological interactions, etc. So so-called lab-on-chip devices are more and more common. Here is another picture which shows just some nano mixing using alternating current to perfectly mix your substance. Also, this picture shows that nowadays it's possible to basically manipulate using electric field the molecules and really selectively transfer one molecule from one place to another and do whatever analysis or reactions on the nano side. Even another case of using electrokinetic processes together with other electrochemical processes is, for example, the quick testing of viruses, because in this case, of course, you don't want to do sequences if you want to analyze 10 million people, right? But you need something which is cheaper, and you can really use, again, the electrokinetic phenomena to transport the virus and at the electrode, and from that signal you can get with some high probability answer if it's the virus you are interested in or not. Water and wastewater treatment, again, something which can mix electrokinetic phenomena with standard adsorption, desorption, coagulation, sedimentation, etc. I'm not saying that all these processes are only electrokinetics, but electrokinetics can be part of it. We can, for example, transport the material or separate it. And as I mentioned, I will end up this talk with applications in desalination technologies. And also soil remediation can use nanoparticles and augmented with electric currents to basically the particles are pumped to the contaminated soil. The particular heavy ions adsorb on those nanoparticles, and then on the surface the nanoparticles can be cleaned, reused, and the contaminant collected. And maybe even 20, 30 years ago, even the people who are not scientists knew about one application of electrokinetic phenomena, and that's electroosmotic dehumidifying. That means that there were electrodes which were drilled to old buildings, and voltage was applied to these electrodes, and it helped really to move the water up and dry the buildings. By the way, the first picture I got when searching for this was from dehumidifying the Astronomical Institute of the Czech Academy of Sciences. And while at old times you really had to drill at each like 2 meters the wall to put the electrode, which is a terrible work, particularly in stone buildings. So this new version uses basically wireless electric field, and so of course wireless has a lot of advantages, at least for some. So let's, after this introduction, let's introduce the topic of transport phenomena. And always, if you have some gradient, it causes some flow, some transfer of some property. And I will start with, if you have a gradient of temperature, then it generates the heat flow, and the ratio between these two properties, that's the heat conductivity. If you have a gradient of concentration between two places, you have a mass transport. The particles move from one location to the other, and the proportionality constant is called the diffusivity. If you have an electric field and you apply it to solution with ions, the ions will move at some velocity, and the ratio of the velocity to the magnitude of the electric field is called the ionic mobility. But not only particles or energy can be transferred, even other properties can be transferred. And for example, you can even transfer the momentum. And if you transfer the momentum in a perpendicular direction to the motion of particles, that generates the shear stress. And the shear stress is related to the shear flow of the adjacent layers, and the proportionality constant is viscosity. So even that is an example of transport, in this case of momentum. And you can calculate this transport coefficient in several ways in simulations. And I will talk about two. One will be the non-equilibrium molecular dynamics, where you really turn on the perturbation, the external force or shear or whatever, and you observe how really your system moves subject to this perturbation. Or you can use equilibrium molecular dynamics, where this perturbation is not turned on at all, but you need the theory and analysis of your standard equilibrium simulations to calculate these transport phenomena. And as an example, which in fact is not the real transport property, but I think it nicely introduces the difference between these two approaches, like equilibrium-like and non-equilibrium-like, I will mention, let's imagine you want to calculate the heat capacity CV of your system. So maybe the most intuitive approach would be something which is in the spirit of non-equilibrium MD, which means you know that the heat capacity is the amount of heat needed to warm up your system. If it's NVT, then there is no volume work, so it's a change of internal energy. And so you might run one simulation at temperature T and average its internal energy, the potential plus kinetic. And then you may run another simulation at slightly higher temperature, get its average energy. And from this ratio, basically, you get your CV. So in principle, it requires just two simulations, and the theory is basically known, right? In reality, it's not about two simulations, because typically you have to do at least like 3 to 5 simulations to find the right delta t. Because if your delta t is too small, then this difference will be very small. This difference will be also very small, and your capacity is determined with huge statistical inaccuracy. If you use too big delta t, then of course both the numbers are statistically fine, but then your CV is not the CV at temperature T, but it's rather some average CV between these two temperatures. We know that CV is not too much sensitive to temperature, but in principle we face these problems. So typically we need to select really several delta T values, and then statistically analyzing these results, choose which time difference is the best. So that will be in the spirit of non-equilibrium MD, I mean turning on the perturbation, in this case heating up the system. Or you can do it in the spirit of the equilibrium MD, and that would mean you just run one simulation at temperature T. Absolutely standard simulation, like if you were just averaging the energy. But you need extra theory. And if you need to derive from the statistical mechanics the formula which will tell you how to calculate this heat capacity. And in this case, it's a beautiful formula and it's easy to derive it. You need to analyze not only the average energy, but also the average square, or in other terms, the fluctuation of the energy. And in these fluctuations of the energy, the heat capacity is encoded. So it's a lovely just one simulation, and you still get the response how the system would react if you raise the temperature without, in fact, raising the temperature. And the same can be applied to the real transport properties. So, for example, to calculate diffusivity, you can have this setup where you divide your system into three parts of your box. Two will be so-called controlled volume. So here you will keep by Grand Canonical Monte Carlo some low concentration of your particles. There will be another control volume where you have higher chemical potential and higher concentration. And here there will be nothing controlled, but simply the particles will spontaneously diffuse from the point of high concentration to the low concentration, and you will measure the flow per some time. And you can think about any virtual plane at which you will count the particles, how much they flow. But in fact, in reality, you even don't need to count how many particles are flowing here, because it's enough just to measure how many particles needed to be inserted here in the Grand Canonical steps, because you simply keep inserting particles and they keep diffusing here. And again, the same number will be the number of particles that you must remove to keep this concentration low. So you see already now the setup is quite difficult. You need to combine molecular dynamics with Grand Canonical Monte Carlo steps. So it's not that easy to determine diffusivity from non-equilibrium MD. But it's much easier to determine diffusivity from the equilibrium MD. Again, you just do absolutely standard simulation without any perturbation, but you need the mathematics to tell you what's this diffusivity. And this is well known that to get the diffusivity, it's enough just to monitor the mean square deviation, how much your particles diffuse over a given time. And you, of course, are averaging this over all possible time starts, and you can average it over all particles of the same kind, and you get a function of this mean square displacement as a function of time. And the theory says that it should be linear, and the slope is twice the diffusivity per coordinate, or 6d if you average the whole vector. So in this case, the equilibrium MD determination is much, much better, and even statistically much better. And at the same time, this works perfectly for bulk systems. If you have complex zeolites, etc., sometimes you need to do the non-equilibrium MD. So there is the third method, how to get these transport coefficients. I will not talk about it, and that you can also get it by integration of the, in this case, velocity autocorrelation function. The theory is well described, for example, in the Ellen Tildesley's book. So let's introduce our system. That's our system, and we would like to see what's the diffusivity not only far from the surfaces. So always the dark blue will be the cation, the rubidium, and the cyan will be the chloride counter ions. And here, in this case, we will have the titanium dioxide, rutyl, which will be either positively, negatively, or neutrally charged. And we can average the diffusivity in layers based on the distance. And the graph will look like this. I said that it should be always linear, but it's linear only due to the diffusive equation. Real particles also obey deterministic Newton's equation for short times. So that's why at short times there is violation, but we can fit it in some range. And for example, this would be the mean square deviation evolution for some layer close to the surface. This would be for layer which is further from the surface and more mobile. And as soon as you are far from the surface, all the slopes will be basically the same. And the first layer basically is immobile and it has a zero diffusivity. So always it's better to average over as long time as possible. But here, if you want to keep it local, it means you don't want your particle to move far away during your time of measurement. We really keep it on the level of only a few picoseconds, this tracking of the mean squared deviation. So from each of these layers, from each of these curves, we got the slope, and then we can plot this slope as a function of distance, as position with respect to the surface. And here is the result. We separately analyzed the perpendicular diffusivity in the z direction and the lateral diffusivity along the surface, and you can see it has quite strange shape, but it will become clear when I add the curve which shows the density of adsorbed water. And you see there's a first layer of adsorbed water molecules with basically zero diffusivity. There's a second layer of water molecules, and there in this high density region, the diffusivity is small. Then we have a third peak, and again in the third peak, the diffusivity is smaller, particularly the perpendicular one, because it's harder to move layer to layer, while it's much easier to move within a layer. And there is an enhanced diffusivity in between the layers. So the diffusivity perfectly anticorrelates with the density. And you see that as close as, I don't know, 15 angstroms from the surface, we have a bulk-like diffusivity equal to the bulk value. And we did later the same work for ions. And in that case, again, there is a huge drop of the diffusivity. This is the same plot in semilog, and particularly the divalent ions, they are very immobile in the last few angstroms, and that can be important for applications like hetero catalysis, when really you need molecules to come to the direct contact with the catalyst. So let's move closer to the electrokinetic phenomena. So again, if you wanted to determine mobility, you can use non-equilibrium MD, for example, turn on the force acting on, for example, one particle and measure its velocity. Or you can try to do it with equilibrium MD, and that means you need some formula which will tell you what's the mobility, ionic mobility. And in this case, we are lucky because the derivation is known for long, and it leads to the called Einstein-Smoluchowski equation, which is a special case of the famous fluctuation dissipation theorem, because you can think of definitely of this mobility like dissipation, because you apply force on particle, but you don't accelerate it because it dissipates the energy to the surrounding particles. And you can think about diffusivity like Brownian motion, typical example of stochastic fluctuation kind of motion. And you can also calculate the electric conductivity. You turn on the electric field acting on all ions and calculate how many ions per second trespass some virtual plane. Or again, you can say, okay, can I calculate it directly from equilibrium MD, just monitoring something without the applied electric field? And again, the answer is yes. And again, it's only the diffusivity of each species which needs to be monitored in equilibrium MD. And if you multiply it by its charge, etc., you get the conductivity directly from EMD without turning on the electric field. But we said we are interested in the motion of colloidal particles. So let's say a few words about what's happening on the surface of colloidal particles, or solid particles in general. So let's say that you have a positively charged surface. So of course there will be a layer of typically strongly adsorbed counter ions, in this case negative ions, and then can be some diffuse layer where both cations and anions are at different concentrations. And this is called the electric double layer. And the screening, how quickly the surface charge is compensated, depends on the concentration of the salt. If you have low ionic strength, few ions to compensate it, your double layer is very thick. and the electric field extends to maybe dozens, hundreds of nanometers. If you have high ionic strengths, your thickness can shrink to basically a few nanometers. So the salt concentration definitely is very important, and this distance can be approximated or expressed via the Debye length, which inversely depends on the concentration and charges of the ions. And now we are going to the motion of particles. So imagine you already have a charged particles, you apply the electric field, and the particle will move. But most particles don't move like Dejo with the naked surface. So it's not this particle surface which would be important, but in fact most particles move like PAL, covered with some layer which shields you. And that's this layer of strongly adsorbed ions. So basically when the particle moves, it's not only this green solid surface, but it moves including this bluish layer of strongly adsorbed counter ions. And also then when the particles interact, it's not the properties here at the real solid surface, but it's rather here, the properties here, between on the immobile and mobile parts of this particle. And that's why when we characterize the interaction of colloidal particles, it's rather not the surface potential, but it's rather the electrostatic potential somewhere here at this also called slip plane, which determines the mutual interaction of particles. And the potential at this slip plane is termed the zeta potential, and it's a big and key property in colloidal chemistry. It typically has the same sign as the surface charge and the same sign as the surface potential, but it's lower because, of course, part of the electrostatic is already screened. So here you can see at low pH, typically the zeta potential is positive. And at high pH, because you have a lot of OH minus on the surface, the zeta potential is negative, and typically it's of the order of tenths of millivolts, and it's zero at the point of zero charge. And it's also important for the stability of colloids, because it's said that if your zeta potential in magnitude will be larger than 20 or 30, it means all your particles are significantly charged. It means the particles repel each other, and that's why the particles don't sediment. They are beautifully dispersed, and that's good if you want to do some scattering experiments or simply interact with the surface of each particle. While if the zeta potential is very small, the electrostatic is not strong enough, and van der Waals interactions can win, and then you have coagulation, sedimentation of the particles, and simply you get some big chunk of particles. So so it's the zeta potential, and the zeta potential, which is measured in these millivolts, is calculated typically from experiments which measure only the mobility of the particles. So what's measured is the speed of the particles, v, u divided by the electric field, and that's the electrophoretic or electroosmotic mobility. And the other constants are just bulk-like viscosity of the liquid and dielectric constant. So this is the key equation which both the experimentalists as well as me use to convert the directly observed mobility to something which is being published like a property of the particle. It can be derived, by the way, this Helmholtz-Smoluchowski equation, just combining the surface electrostatics, the shear flow, the capacitor, etc. And the result doesn't depend on the location of the layer. Simply, it's the electrostatic at this layer of mobile ions. So my first approach was trying to get the zeta potential directly inspecting the electrostatic profile, because it's reported in millivolts. So somewhere at the interface we should see some point where we can read 20 millivolts. But in fact, it turned absolutely impossible. The lines are shifted by 2 volts, but if you look here, you see you have oscillations of the order of 1 volt. and maybe somewhere here far from the surface you might reach the millivolts, but then you have either oscillations or continuous change, definitely no point where you would easily be able to read the zeta potential. So I decided to do directly the simulations of electrokinetic phenomena. In principle, I could do the simulations of electrophoresis, but that would mean I would have to have one huge particle, maybe made of 1,000 or 10,000 atoms, and I would be monitoring just the motion of one particle, which would be absolutely terribly huge system and terrible statistics. So it was much better to do the simulation of electroosmosis, where I have immobile surface. I can average the motion of a lot of water molecules, and I have very good statistics. So that's why I was modeling the electroosmosis. And this is the view of the interface. So I have electric field along the surface. So of course the blue cations will move in the direction of the electric field. The cyan anions will move in the opposite direction. And the highly non-trivial question is, will there be any motion of the liquid far from the surface? Will the water flow? Because of course the net electric force acting on neutral water is 0, right? So I started these simulations, and on top you can see, and now I have problems with the movies which worked when we tested it, and they don't play. So I will talk in the meanwhile. So we will have first a negatively charged surface. So the interface will be dominated by positive counter ions, and the counter ions will move in the direction to the right. Yes, thanks. And please, Jonas, now watch just at the top movie. So we have these cations, blue ones, which move to the right, and there is a majority of counter ions compensating this negative charge. And there are the anions moving in the opposite direction. What you can see is that in fact the water flows to the right, with the majority with the cations. And because it's electroosmosis, there is extra negative sign. So we have positive mobility, but the zeta potential is negative, and that's correct because the zeta potential should have the same sign as the surface charge. And then if we do the same for positively charged surface, you see that the interface looks very different. We have a surplus of anions, they move to the left, and they drag the water molecules with them. So we have negative mobility, and negative mobility converts to positive zeta potential, and again, that's how it should be for positively charged surfaces. So that was a good test that we can model the electroosmosis. And we can measure not only the relative motion of the liquid far from the surface, but we can even look what's the mobility of cations and anions and water as a function of distance from the interface. So very close to the surface, everything is adsorbed and immobile. Here you have this inhomogeneous region where the mobility of the ions as well as water relative to the surface builds up. And then you end up in a region which is already far from the surface, where the ions move with respect to the water with normal ionic mobility. But what's important, the whole liquid, all water, even far from the surface, moves at non-zero speed. And this is something which I find fascinating for electrokinetic phenomena, because it's a surface-induced phenomenon which affects the motion of a whole big volume. So even if you have a millimeter thick capillary, and there would be some charge imbalance only in a few nanometers, the whole millimeter volume of the capillary will flow. And by the way, that's also one application of electroosmosis. If you want to dosage 1 microliter, you turn on the electric field, and from the capillary you will get 1 microliter of liquid. Another example to better understand this, because this is, I have experienced typically difficult to understand, that really the whole fluid, even far from the surface where you already have charged negative flows. Imagine that you sit on a river of a bank and you have a lot of friends, and all of you start to paddle the water next to the bank, just in the first meter. And if you do it for a very long time, and if you forget about the friction of water with the riverbed, the whole river would start to flow even far from the bank where no one paddles. And that's exactly what's happening here, that the driving force is only at the interface. One short comment on the magnitude of the external field. In this work, we used the electric field, which was 2 to 10 times 10 to 8 volts per meter, which is something like a megavolt per centimeter, while in simulations typically a volt per centimeter is used. So why do we use such a strong field? The main reasons to have statistically meaningful results, because in experiments you can average 10 to 23 particles, while here we have hundreds of molecules in each layer. And here I show that we monitor this streaming velocity of the liquid as a function of distance. And at each distance, the velocity of any, let's say, water molecule has basically 2 components. One is this streaming velocity, the oriented flow, and the second is the thermal motion, and that goes with the velocity, which is of the range of mean square velocity, and for liquid at room temperature, it's plus minus 370 meters per second. So of course you need some signal. And we simply selected the electric field to be so big because the magnitude of the electrosmotic mobility you can't choose. That's really the property of your system. And it's so small that simply only when you use such a big electric field, we end up at the average velocity, which is of the order of volts, and we can measure it. We can go 10 times slower and measure 0.3 plus minus 370, but we definitely cannot measure at 1,000 times smaller, which would be still 1,000 times larger than in experiment value, because we can't average 0.003 plus minus 300. It's simply impossible in the size of the system we used. So that's why we use such a strong field. But as long as the field is in the linear response regime, it means that the response is proportional to the stimuli, then we are safe, and we tested that in this case it was okay. So we can measure the streaming velocity, we can see that it's positive, negative, etc. And we can then report the results, and we directly measure the mobility as a function of the surface charge, but the experimentalist as well as us convert the mobility to zeta potential. The experimentalist immediately directly measure what's the pH. We used the pH titration data to convert the surface charge to pH. So we can report, like in the experiment, zeta potential as a function of pH. And here is the result. And already the first results for rubidium chloride were excellent because it has the right shape, going from positive to negative values with pH. It has the right magnitude. And also, if you decrease the concentration, the signal gets stronger. What I indicate here by zero mole means basically only counter ions. So if it's positively charged, I have only chlorine. If chloride, if it's negatively charged, I have sodium. If it's uncharged, I have literally 2 or 6 pairs of the salt. Then we did simulations for sodium chloride, and the first simulations for sodium chloride I got were these. And I was wondering for several months what's going on, because it definitely doesn't have the right shape. It stays positive even at high pH. And only I became a bit confident in my simulations when I did it again only with these counter ions, when really the shape became in fact in very good agreement, and even the values with the experimental data. So we got the agreement basically with experiment, at least at low concentrations. But the huge advantage of simulations is that not only you get the results, but you get the molecular view, and you can deduce the origin of the phenomena you see. And so in this case, we have seen what's the difference in case of sodium. And first of all, we were lucky to find these experimental data, because most titrations are done at a really small concentration of salt, but there is this acoustophoresis which can go to basically molar concentration. So there are also experimental data which see that the zeta potential at high concentrations, like we used in our simulations, can stay positive throughout the pH range. Then we did the same with divalent ion. Again, instead of going down at high concentration, it even went up. But we found also simulation at high concentration of another divalent ion, calcium chloride, which also show that it has this anomalous behavior, that the zeta potential can stay positive throughout the pH range. And here's the molecular explanation. And again, the movie's fine. We need to look at the bottom one. So we have seen before the top one, which was rubidium. And now on the bottom, you have also negatively charged surface, but sodium. Sodium is smaller. It absorbs stronger. It can interact stronger with the surface. So in fact, there is more adsorbed sodium than there was rubidium for the same surface. But you can see most of the sodium is so tightly adsorbed that it cannot move in spite of being subject to this electric field. And so then there is this majority, few counter ions, and in fact, it's these counter ions which rule, which go to the left, which drag the water molecule with them, and that results in a negative mobility, which converts the positive zeta potential, and that's exactly what we have seen in our simulations, and that's this anomalous behavior. So we have explained the origin of this anomalous behavior, and it's related to overcharging of the surface. So I think I'm running out of time, so I will probably skip many slides, and I will just show that currently we are studying the adsorption and flow through graphene-based nanopores. We study different nanopores with different height, with different lengths, and the behavior really differs. It can be like 7, 9, 12 angstrom height. It can generate several layers of water and ions. And here I will show, and these pores can be easily manufactured, because you basically take a piece of graphite, use few layers of graphene as a spacer, you cover it again with graphene, and here you have electron microscopy photo of a perfect graphene nanochannel, and if you have a battery of them, you can even do the flow experiments on them, and it's done in the National Graphene Institute in Manchester. And we currently are working on the application of these nanopores to capacitive deionization. And let me just describe that here we have a very thin nanopore, which is rectifying so strongly that if it's negatively charged, only positive ions can enter the pore, and it's basically impossible to go through for the cations, and the opposite is here for the positively charged surface. Only anions can go through, and if we turn on the electric field, I think it was so fast that I will try to run it once again. If you turn on the electric field, the positive ions will move through this channel to this reservoir. The negative ions will move in this direction through the positively charged channel, and at the end up you do really this capacitive deionization that you basically remove all the ions, and you end up with less salty water, or basically desalinated. So because I'm sure I ran out of time, I will end up here. I wanted to show, I have a couple of slides showing the artifacts. If your electric field is too strong, maybe we can leave it for questions, but I think it's time to thank you for your attention.
Thank you very much, Milan. It was very interesting, great talk.
Sorry, it's I assume that students should ask questions, but I just wanted to have some clarification, because you were speaking about electric fields, and if you have, for instance, 2 electrodes and separate by electrolyte, you cannot have a static electric field, because it will be screened by the double layers, and the bulk will be neutral. in order to have a static electric field there, we should have a flow of ions, background maybe ions, apart from your colloidal particles, and then they should react electrochemically of those electrodes. Then there will be a continuous current, and that continuous current will give you a ohmic drop. Ohmic drop will give you electrical field, like that. So when you're speaking about static electric field, do you mean exactly like that or something else?
I think there is not a big difference between the experiments and simulation in this. Of course, for us, it's simply extra force we just turn on, and it's so easy to turn on.
It does not.
But you mean like the electrophoresis setup? So it's really, in ancient times, it was done really that there were two electrodes, and there was a static field with basically constant gradient between the two electrodes, and really the people were watching the particles as they move. They were monitoring on some CCD cameras, and of course the field is screened, but you simply have the voltage difference, you have the distance, so it's clear what's the electric field. So honestly, I don't fully understand what would be the problem, because really there was a constant static electric field. Of course, there were some reactions happening and electron transfer at the electrodes, but in the volume between the electrodes where the experiment is done, it was really constant field and constant speed, of course, plus minus thermal motion.
Be there, but not if you have a blocking electrodes, right? If you don't have electrochemical reactions at the walls, then after you apply voltage, you will settle the double layers, but the bulk will be electroneutral. And so your motion of the particles will be diffusive, simply random, and then it's sucked at the double layer, but the double layers are narrow. So in order to have a permanent field like that, you need to have a permanent current, continuous current, in which ionic current is transferred into electronic current, like that one. So that's called an ohmic drop, like that. Your ohmic drop will give you the electric field. And because of that understanding, I want to also understand when you apply very large fields, how they're related to this kind of overall phenomenon, because you have to consider the whole system, right?
Yes.
We
are lucky in this case that we use non-dissociative models of water, so even strong electric field cannot break our water molecules. So that's to some extent advantage. And maybe I will just show here this slide saying that here I see for example, the density of ions in the pore and outside. And you can see here we used even weaker electric fields. And this purple one, that's definitely the strongest one. And in this case, I would say it's the only one which already introduces artifacts. For example, this is positively charged surface. There are no ions in it. But if you have so strong field, you start to have ions there. Or here you see the density profile of chloride. If the field is weak, basically the structure is independent of the electric field. If the electric field is too strong, you start to really deform the shape. So we take care of this. Of course, always there is at least some effect of the electric field. Simply water orients always if you turn on electric field. So we are doing our best to use as small electric field as possible, but of course it's 5 to 6, 7 orders of magnitude larger than in reality.
Okay, but the origin of that electric field should be associated with the current which goes here, ohmic current, because otherwise you will not have electric field in the bulk.
But we use periodic boundary conditions, and the electric field is simply applied a priori, simply like external field. So we don't need to have the physical electrodes in our system.
Yeah, I understand. In simulation, you can do that. But in reality, you have to relate a voltage drop and electric field through the current and through electrochemical reactions taking place at the interface.
Yes.
Thank you.
Thank you very much. When you were using, I suppose you are using full-scale force field. So I saw on a negative surface, sodium is strongly binding. So in that case, what was the selectivity? I mean, aren't they overcharging? So
With full charges, definitely it was sodium was overcharged, but in fact we published several papers on this, and in the later paper we also scaled charges, and we also compared the absorption and zeta potential behavior at TiO2, which is strong adsorbent. So you see this anomalous behavior of zeta potential with the pH, and we compared it with quartz, which was modeled with scaled charges, and there the behavior is absolutely standard. So definitely the model, if you how strongly the ions adsorb, are the key factors which affect also the behavior of the zeta potential.
What was the effect of electric field? Like the selectivity was changing?
You mean the magnitude of the electric field?
No. If you change electric field, so it might have different effects on cation and anion. So they might have different movement or the flux. So did that change the selectivity with respect to electric field?
I think we should discuss it in privately, because we always report the result of both ions. I cannot exactly say how change in the behavior of cations and anions contributed, but in fact at this extreme pH, basically it's either purely cation dominated or anion dominated.
Then how much was the thickness of that stern layer?
Typically, it was really up to 15-20 angstroms from the surface, because we typically used concentrations up to, let's say, 0.4 molar. And even what I call 0 molar meant that we needed to have counter ions, which were basically at the concentration of something like 0.06 mol.
And I see that the electric field is around 0.2 volt per nanometer. How do we compare that with some experiment? Because the electric field that we are using is around 0.06, and the size of my cell is around 18 nanometer. So we still think it's too much.
Of course, it's much, but I have seen to average the streaming velocity, I can't go much lower. Of course, some of these results are already a few years old, so we can go a bit lower. Once again, it's of the order of, let's say, 10 to 5, 10 to 6 volts per centimeter, while in the experiment, it's 1 volt per centimeter.
Okay, thank you.
All right. One more question? Short question?
And you assume that Cepher charge is uniform, yeah?
No, definitely not. It's a realistic charging. So, for example, if you want to make the surface charge negative, we adsorb more OH minus groups on the surface. And if you want to make it positively charged, we add hydrogens to some of the surface oxygen. So there are specific atomic charges on each titanium, oxygen, hydrogen ion, and they even change. It was calculated by ab initio, so it's really atomistic charging. There is nothing like just monotonous surface area, surface charge.
So you just only could say that it's positively or negatively charged, but not with more details. Yeah.
Yes, I wasn't talking about the details of the model, but yes, I report just the average surface charge density, which results from the atomic.
Okay, thank you very much, Milan. It was a great talk. Thank you for your attendance.